the light ray is reflected, and the other part goes through the surface. And as you can see, let's just set there. Okay, this is a little better. You can see that the light ray is bent as a result of interacting with the material. And the reason that it's bent is that in going from one material to another material, it changes the speed of the light ray. In this case, going from air to water has caused the light ray to slow down, and that slowing down causes it to actually bend toward the normal, which is this perpendicular line. Okay, so, okay, let me go ahead and bring up the camera. Okay, so I'll look at the document camera. Okay, so all right, so we're looking at refraction, only now we're going to look at the other case for refraction. So this is refraction of light part 2. Okay, and in this case, last week we looked at what happens if we're going from material that has a smaller index of refraction to a larger index of refraction. This week we're going to go from Ni is bigger than Nr. So we go with an optically thick material into an optically thinner material. So again, we have some kind of an interface. We have the Ni here is the index of refraction of this material, and Nr is the index of refraction of the other material. And we have a light ray that comes in like this, and it strikes the surface. And then if the two are equal to each other, it would just continue straight. So I'll draw a little dotted line here. Let's see if maybe I can keep it from being so bent. Let's see. I think that's a little better. Okay, so this is the way it would go if Ni was equal to Nr. Okay, and there are two possible ways that the light ray can be bent. It can be bent to something like this, okay, or it can be bent like this, okay. We did the purple case last week. This is for Ni less than Nr. Okay, and this week we're going to do this orange case, which is Ni bigger than Nr. Okay, and the idea is that we're looking to measure angles. So if we're wanting to measure the angles, I want to measure the angles with respect to the line that's perpendicular to the surface. So this is perpendicular. This line that's perpendicular to the surface is known as the normal. Anytime a mathematician, or I guess a physicist, talks about the normal, they mean it's perpendicular. I'm not sure why normal is perpendicular, but I don't know. They didn't ask me. So, okay. So we measured. Yes. Did somebody have a question? Nope. Okay. I think somebody's just, I don't know, doing something. Oh, you know what? I need to set this so I can put it on the. I completely forgot to put it on the chat, so I can see if anybody has any questions or anything. Go away. Okay, move this here. Okay, so we were measuring angles, so we measured this angle in here, and this was the incident angle. Okay, and this week we're going to be measuring this angle here, which would be the refracted angle. And then the idea that kind of connects all these together is known as Snell's law. Okay, which says Ni sine theta I is Nr sine theta R. Okay, so in this situation, we're going to be going into air. So our NR here is going to be the index of refraction of air, which turns out to be like 1.000, and then you have some numbers there. So to 2 decimal places, or to 3 decimal places really, we can say that the NR is equal to 1. So I'm going to go ahead and put that in here. So I have NR as 1. So I can write Snell's law as Ni sine theta I is equal to sine theta R. Or I can solve this for Ni and I get that. Okay, so this is the equation that we're basically going to be using to look at, or the theory basically we're going to be basically looking at. Now I want to note, put this in red. Okay, last week we used NR, which is equal to sine theta I over sine theta R. Notice this week it's reversed. Okay, so if you make a mistake and use this, the sine theta I over sine theta R, you'll end up getting an index of refraction that's less than 1. Remember, for most usual ordinary materials, the index of refraction should be greater than or equal to 1. If it's less than 1, you have an odd material, like a plasma, for example. An ionized gas can have an index of refraction that's less than 1. You can also have waveguides, just different odd things out there. If you're just talking about what we're doing, which is glass and water and transparent materials, then your index of refraction is typically bigger than 1. Okay, so this should be kind of a clue. If you get an index of refraction that's smaller than 1, you're doing something wrong. Okay, not to beat a dead horse. Okay, so the other thing I want to do, in addition to kind of using this, we want to do a graph. Specifically, I want to do a graph where I look at sine theta R, and this is equal to Ni sine theta I. Okay, this one, we're plotting this on the y-axis like we did last week. We're plotting this on the x-axis like we did last week. So what that means is that the slope here should be equal to Ni. Okay, last week our slope was equal to 1 over Nr. So that's the other thing that's different about this week compared to last week, is that our slope here is just equal to Ni. And then of course the y-intercept is just, theoretically it should be equal to 0. In reality, it will probably be something that's small, whatever small is. Okay. Okay, so I'm going to stop for a minute, give everybody a chance to catch their breath, catch up if you're taking notes. If you're ready to go on, if you would say so, but in the chat, or just say ready, so I'll know, and then we'll go on from there. So Alejandro said he's ready. He's on top of his game. Melanie Slayton, all right. Wow. Everybody's on top. Everett, Arturo, okay, so, well, Devin. Well, if Devin's ready to go, then everybody must be ready to go. Okay, so, sorry, Devin. Okay, so to do this, I'm going to use, okay, I'm going to go back to, this is actually a spreadsheet. This is actually a LibreOffice spreadsheet that I created when I was initially creating the lab. But it's more or less the same thing like what we had last week. Maybe it's a little different, okay? So, yeah, it's more or less the same, okay? So what we're going to be doing this week is, first of all, this is on Ray. Okay, we went from air to water. Okay, now I want to reverse this and go from water to air. So if I click on this and change it to water, and I'll click on this one and change it to air. Okay, and you'll notice this actually hits the surface and it bounces up. I'll come back and talk about this in just a minute. For now, if we move this to, I guess, smaller incident angle, like this, Okay, and again, we're going to use our protractor. So we set our protractor up like that. Okay, and then for this one, we're going to start off at 10 degrees. So I'm actually going to start off there and then work up from there. I think last week we started from 20, and there was a good reason for that. And if you really want to know, I can tell you. But this week we're going to be starting at 10. So in fact, let me go ahead and bring up, oops, the data table. Okay, so this is what the template for the data table looks like. Okay, so there. So again, we're starting from 10. Okay, this time I'm going to show you how to put in the Greek characters. I'm also going to show you how to put in subscripts. Okay, so that'll be one of the things that we'll do as we're going along. So, go back here. Okay, so I'm starting off at 10. Okay, I'm starting with the spreadsheet that I used last week. And the reason for that is that the equations are almost the same. Okay, so I'm being lazy and I'm basically just going to use the work that I used last week. And I would encourage you to do the same thing if you have it. Hopefully everybody saved it. I should have told you all to do that last week. I made a point of telling you to do that. And this is, again, one of the really nice things about using spreadsheets or computer programs is once you've written one and it works, you should save it, squirrel it away somewhere, and then if you run up into another situation where you have to create something that's similar, well, you've already got a lot of it already done for you. You don't have to go back and redo it all over again. Okay, so I'm just going to get rid of these because these are now going to change. Okay, you notice all these did weird things. We'll get to that in a second. Okay, so, okay. I think before I do this, I do want to go ahead and, no, actually not. I'm not going to change this here. I'll come back to that, sorry. Okay, so I'm going to go back to this, and I want to put it at 10 degrees. Okay, and to me, this looks like it's at 15. So I'm going to go over here and say my theta r is 15. Oops. Oops, I don't know where I put in that 15. Let's try it again. Okay. And you'll notice my NR here is less than 1, so that's a problem. We'll come back to that in a minute. I'm going to go ahead and finish taking a few more data points. So there's 10, there's 15, so that's going to just a shade above 20, so I'm going to say it's 21. And I'm going to do 20. Okay, and that's like 25. I'm going to say it's 27, so it's roughly in that neighborhood. And do a couple more. Okay, and then 25. That's going to come out to about 30. Actually, it looks like it's exactly 35. 30. Let's skip some. No, put it 30. Like that. And that's 40. I'm going to say it's 44. Okay. I'll let you fill in the rest of these. Now, at some point, if I keep going to larger and larger angle, okay, this ray in the water, the refracted ray, actually disappears. So it disappears at, well, about between 45 and 50 degrees. So on the data table here, I've only gone to 45. So that may be something that you have to adjust from last week is, I think we did up to 70, and we also went from 20 to 70. So you want to change these numbers in here to go from 10 to 45. And it means we're doing 3 less than we did. Let me do this. So I'm going to, just so I can show you how to do this. Okay, so just a second, the lights went out. Oh, this is pain. Okay, so this was, okay, 60, 25, 30. Okay, and then we had all these in here. So I want to basically change these, so this one starts at 10 now. So 10, 15, 20, 25. I want to get rid of these last few here. So if I just highlight these and then do right click and delete rows, it gets rid of them and it shifts those others up. Excel, if you use Excel, it may ask you, do you want to shift the cells left or right? In this case, you want to shift them up. Okay, so I have that. So this is converting from degrees to radians. We don't have to change that because that's not changing. I have sine theta I, sine theta R, that's not changing. Here though, I'm not doing NR, I'm doing NI. So I want to change this to NI. And then here, instead of doing sine theta I over sine theta R, I want to do the reverse. I want to do sine theta R divided by sine theta I. So I'm going to go back here and change this so it's this one divided by this one. And when I do that, now I've got something that is bigger than 1, so that's good. Okay, go ahead and do that. And then just going to get rid of. Okay, and you'll see that, okay, now it's calculated these. So in fact, this is the average value from 5 to 9. And this is, actually, this is looking at 10. Why is it looking, oh, because I have a value there. But I don't think, well, let's actually correct that. So this should be going to, how do you shift the cells up again? Actually, let me do this. Let me copy this and put it in Excel so that yes, whatever. This one is C4. Okay, and I'm going to, yeah, do that. Okay. Okay, so I'm going to insert the cells here. So I'm going to insert and insert and insert. And then these started at 20, so this was 20, 25, 30, 35, 40, 45. Okay, and I want to start these at 10, so I'll go up here and do 10, 15, 20. These last three I don't need. So if I go over here to the side where it says 13, if I click on this and hold it and then drag it down so it highlights those 3 cells or those 3 rows, and then I can do a right click and delete. Okay, and then it just shifts everything up. Okay. 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 You're welcome, Bonnie. Okay. So let's see, I have those values. Let me double check to see. Oh, it actually isn't. So we'll go ahead and put in the formula. So this is going to be our average from here. And again, you're going to want to do the average. Actually, I want to look at something. It's 1.3898. I'm wondering, go down to, okay. So this is actually a useful thing. I just wanted to double check to see if I was right. What I did was I started off by just telling it to take the average of these. Okay. And then I went back and said, okay, now I want to take the average of this all the way to these last 3, where the last 3 are just blanks. And the average function in here is smart enough to know that if it's a blank, then you don't count it as part of the average. So it basically just took the average of just these numbers here. So it divided by 1, 2, 3, 4, 5. So it added those up and divided by 5. If I put in 3 more values here, then it'll add those to it and then divide by 8 rather than by 5. Okay. So this is a good reason why to use the actual functions, because there's a lot that's built into the functions to make adding data like this easier. Okay. So I'm betting you, in fact, yeah, I think everything else is probably okay. But I do want to do percent difference. So let's do that percent. This is the water case. Oh, that's right. Percent difference, it's going to be 100 times the theoretical value, which was 1.33, minus my average value. Oops. An equal sign there. Let me try that again. Average. Okay, I have a 4.96%. The fact that it's negative, yeah, I don't really care. Really, and that's actually kind of high for this one. Probably should have been a little bit more careful when I was making my measurements, but it's not bad. It's not bad. Okay, so let's see. I think. Okay, so I think. Okay, so I'm going to assume that the spreadsheet is good. What I want to do now is copy it and paste it into a Word document. Before I do that, I want to give you all a minute to catch up, ask any questions. How do I shift this? Okay, no, it's Bonnie already answered Bonnie's question. Sorry.
We're changing NR to NI.
Could you say that again?
So we're changing NR to NI?
Yes, and in fact, I should fix that in these as well.
And I've got a 45% difference.
That's odd. Did you multiply by 1,000 or by 100?
Let me check.
That would be my first guess.
I didn't change anything.
Sorry. What did we change on the simulation again? On the simulation, okay, last week we had air to water. Okay, this week we're switching it. So I want to have water up at the top and have air at the bottom. Okay, so that's what's different there. Okay, and I think I fixed my spreadsheet. Okay. Does anybody else have any questions? Okay, so actually I'm going to give you all a minute to catch up. So when you're ready to go, just type in ready or say ready and let me know, and I'll move on from here. Alejandro's ready. He's on top of his game.
Would you mouse back over the equation or the formula for percent variation? Because my numbers.
Percent variation? Okay, it's just, okay. It's, okay, let me, I actually don't, I just copied the numbers. Let me put in the values. So this is going to be
okay.
ST.S, and from this to, that looks a little better. And then this would be, this one I actually have to, that in square root of 11. Right now I only have, 8 values. What did I do? Oh. But if you put in the other 3, then that'll give 11. So your number should be a little bit bigger than this. And then there's,
Yeah, they're around.
Sorry?
I was saying, yeah, those are closer.
Okay. And then percent difference. Okay. So everything else should be good, I think. Okay. How do I get sig figs to 4 decimals? Okay. Abigail. So I'm going to click on like my column I here. Okay. And if I do a right click, okay, I can do format cells. Okay. You can also, if you're in the home tab, go to format here, and then you want it to format cells, and then you want to go to number, and then tell it the number of decimal places, okay? Are you using LibreOffice, Abigail, or are you using Excel? Excel, okay. So this should do it for you then. So does that work? Okay. Anybody else have anything else?
So your NI equation is sine theta I over sine theta R.
It's the other. It's sine theta R over sine theta I. In the one last week, it was sine theta I over sine theta R, but you have to change it this week.
Okay, that's what I missed.
If you're doing it correctly, you'll get numbers here that are bigger than 1. If you have numbers here that are smaller than 1, you've got a mistake. For percent variation, can you show the equation? Yeah, actually, it didn't calculate the number, did it? So this is, it was 100 times the uncertainty divided by the average value. Okay, so hopefully that's better. Oh, and let me, there. Okay, anything else? Okay, nobody's saying anything. So what I'm going to do is I'm going to copy these into a Word document, and then what I'm going to do is I'm going to change like the thetas and put in the subscripts in the Word document. You can put them here in the Excel document, and if you really want to see that, I can show you. It's not hard, but it's easier to do it in the Word document. So that's actually where I'm going to do this. So I'm going to copy these. So copy and go open Word. Your phone, that's kind of scary. Sure, why not? Okay, I want to put in my title here. Put in my data table. So I believe it was the second one that puts in. Okay, so there's that. Okay, so remember we can adjust the size of the columns. So like these, actually, I wonder if I can do that in here. No, it doesn't. So I'll just leave it. So clean this up a little bit. When I change the thetas, I'll get a little bit more. Okay, let me just go and do that. Okay, so here I want to get rid of this theta I, and I want to put in my Greek character theta. So if you go to Insert, and way over here it says Symbol. So if you click on Symbol, and that gives you kind of a list of the commonly used symbols. Theta is not one of them here. So I'm going to click on More Symbols, and then I want to look for the Greek characters. Where are the Greek? Greek and Coptic. There we go. And then I need to scroll down a little bit, and there's my theta there. So I'll do that. I'll put that in there as well. For those of you that know a little bit about Unicode, you can also do the Unicode and various other things. I'm just learning about that myself, honestly. So there's that. And then I want to put in, let me make this a little bigger because I can't see it. Actually, I need to shrink this down so I can see comments. Okay, so there's theta. I want to make this theta sub I. So I'll put in an I, and then I want to, I'm going to go back over to home. I'm going to highlight this I, and then up here I have subscript, superscript. So I'm just going to click on that and make it into a subscript. Okay, and then here, actually, yeah, okay, kept it, and then highlight that. And I think I'm going to cheat, actually. I'm going to do Control-C to copy it, and then I'm going to highlight this and go Control-V to paste it. So I don't have to keep switching back. Those keyboard tricks are kind of useful sometimes. Okay, and then make this here, these need to be, oops. Excel has this annoying habit of, I don't know why it does that. It's just annoying. Okay, fine. That, and then I'll do this separately. There. And then here, I want to replace this D with the Greek character delta. So I'll get rid of this. Go insert symbol. And I'm not seeing a delta, so we'll do more symbols. And there is my delta there. We use a small capital delta, or small letter Greek delta for uncertainty. That's what we used last semester, so that's what I'll put here. And then I guess I should go ahead and do these as subscripts as well, just to be complete. Okay, so that's going to be the data table for water. So I probably should put in. Okay, so you'll have that. And then you're going to want to do a graph just like we did last week. We're going to do these values will be the y values, these values will be the x values. So you'll do more or less the same thing that you did last week on that, which is good. The idea here is you're doing a lot of the same things over and over. Repetition is about the only way you can really get something into memory, is doing it over and over again. So that's part of the reason why we're kind of doing a lot of stuff over and over and over again. So the hope is when you get out to the big bad world, you'll know how to do this and you won't have to think about it. You won't have to look it up on YouTube. Okay, so is everybody okay so far? Anybody have any questions? If you would, let me know when you're ready by typing in ready. Slayton, ooh, Alejandro, Slayton beat ya. Coming in second there. Oh, yeah. Didn't know it was a race, did you? Slayton, I shouldn't really make this a race because I'm afraid people will just, not be doing the work with me. But it makes it fun. So it's all about making it fun, right? Okay, I get a couple more. Don't want to rush through this too fast. Oh, Arturo, I just saw you. I'm sorry. Are the numbers random, or should be getting similar numbers to yours? You should be getting, in here, you should be getting numbers that are around 1.3. So your theta R's are probably going to be a little different, although they may be the same. But you're going to be filling in these, and then you'll get these numbers in here as well. So remember, the index of refraction for water is 1.33. So you should be getting something that's around that value. So if you're not, you might be doing something wrong. And if you're having trouble, let me know, and we can maybe sit down and look at yours and see maybe what you're doing wrong. Does that answer your question, Giselle? Yes, okay. Okay, anybody else have a question? I want the lights again. Any other questions? Okay, I want to go back to the data table for a second. Data table, here we go. Okay, so the next part of the data table is this total internal reflection of water. And I want to talk about what that is. So this is the idea is that if you keep increasing the angle, eventually you get to a place where the refracted ray disappears and the ray basically is hitting this surface and all of it is bouncing back, okay? So the ray is, in essence, it's trapped inside the material. And then if you had, say, a similar interface up here, the ray could hit that, and if the angle's right, it'll bounce off that as well. So the ray basically bounces away inside of this material. So this is the principle behind fiber optics. You have basically a transparent material. You want it to have a really high index of refraction. The higher, the better. And I'll show you a little bit more on that in a minute. And then the higher it is, the better it is at trapping light. And then you can use this basically to propagate signals from one point. You use light basically from one point to another over around curves and various things like that. Okay, so I want to go over kind of the theory for this real quick. So I'll do that on my next page here. So this is total internal reflection. Okay, and this only happens in the case when Ni is bigger than Nr. Okay, so what's happening here, again, this is Ni, this is Nr, here is R. Okay, we have a light ray coming in, okay, like this. And if this angle here is it's what's known as the critical angle, so we'll say this is theta sub c, then what happens is that the light ray is basically refracted at 90 degrees. So it's basically going along the surface like this, okay? And then anything that's bigger than this critical angle basically just bounces off of the surface. So this is the spot basically where the light goes from escaping to being trapped inside the material, is what the critical angle is. So here, my theta r for this would be 90 degrees. Okay, so if I go into Snell's law, so again, remember nr here is 1 because it's the index of refraction of the air. So I have ni sine theta. I'm going to put sine theta critical is equal to r, well, just put nr times sine theta r. Okay, theta r, remember, is 90 degrees, and the sine of 90 degrees is 1. Okay, and then remember nr itself was equal to 1. So if I put this all together, I'm going to get ni sine theta critical is equal to 1, or sine theta critical. And incident is 1.0 divided by the critical angle. So if we determine what this critical angle is, then we can just use this expression to get what the index of refraction is. Fortunately, we can only measure this once, basically. So it's just going to have just a very simple little piece here on the data table. Okay, you basically determine what the critical angle is in degrees. You convert that into radians, and then you use the formula that I had there to get what Ni is. I forgot, oh, no, keep that one. That one's okay. Okay, so to actually measure this in the simulation, okay, so the idea is we start off here, and we increase this, keep increasing this, and slowly, it's right in there. There, okay. So I would say that that is 30, 40, 45, maybe 48 or 49 degrees. Okay, so if I go over to here, I want to create just kind of a little piece down here where we have theta. C, and this is going to be in degrees. Theta C in radians. And then I'll have, this was, I think I said it was 48 degrees. Okay. So remember, to convert from radians to degrees, I want to do equals, and I want the number in degrees times pi, open parenthesis, close parenthesis, divided by 180. And that converts it to radians. And then here, I want to do equals 1 divided by in radians. There it is, 1.345. Okay. And again, that's a reasonable number. It's bigger than 1. That's good. It's also around 1.33, which is the index of refraction of water. So that's good as well. So what I'll do now is I will copy this. Okay, and then down here, I'll put in, let's see. Just going to do paste. Okay, and there's the data. And then you want to go in, again, pretty this up. Okay, but the information is there. I also asked you to calculate a percent difference. Actually, I probably, what did I just do? Okay, you probably just put that, actually I have it off to the side. Quit. Probably just put it here. So percent. You can just use a calculator to calculate that if you want, or if you want to do it using Excel, that's fine too. Whichever you want to do, since it's just the one number. Okay, I would like you to use Excel or your spreadsheet to do this part and then paste it in there, again, to practice it. Okay. Okay, is everybody okay so far? Anybody have any questions? Okay, if you would, let me know when you're ready to go on. Typing ready, or saying ready, or whatever works for you. Alejandro, ooh, Slayton, he's getting to you. He got you, Slayton. He was rating there. He was hovering his hand over the enter key. It's like, what was it, Jeopardy? Where they have, it's the race to see who pushes the button. Okay, Arturo says he's ready. Good. Thank you, Arturo. And Melanie says she's ready. Good. Can I get one more? And Devin's ready. Okay. All right. So let me go back to the template here for a second. Okay, so then we've got the graph. Okay, so hopefully that won't be too bad. Then, okay, for the next one, I want you to basically repeat the same thing, only with mystery B. Go back to the simulation. Okay, so here, I want to change water to mystery B. Okay, and you may ask, well, why aren't we using, no, mystery B. Okay, mystery B. Why aren't we using mystery A? Well, if you look at mystery A, the index of refraction is so large that basically we only get to about maybe 25 degrees before it's totally terminally inflected. So we're not really going to get much data from that. So we'll just go to mystery B where we can get a little bit more data and work from it. Okay. And again, the idea here is to you start from 10, And then it looks like that's about 15, then you go 10, 15, 20, record the various angles. Again, reuse your data table. Okay, so you could just copy this. What I'll do is I will just copy this. Actually, I don't think I can. Yeah, I can't really do it because it copied the values. But if you have your one from last week, you can just copy it and then just paste the new values of theta r in here, and it should automatically update these as well. Okay, so there's that. The next piece, I think. Okay, so that's this. Okay, and again, I can't ask you to do a % difference on this because we don't have a theoretical value to compare to. We don't know what it is. It's a mystery. So that's why, it's a mystery. Okay, and then I want you to go ahead and do the total internal reflection for the two mystery cases as well. Something I do want to point out here, I want to go to mystery A for a second. Okay, so the reason I want to show this is this has a very, I guess, small critical angle. Okay, so what that means is any light ray here that comes in and hits the surface at any angle in here is trapped inside the material. Okay, so you can think about if the light ray is coming in, it can come in, nothing's going to stop it from coming in. Okay, but once it gets inside, it's actually really hard for it to get out. If you think about the probability of it hitting the surface, it has a lot more of a probability of hitting it somewhere in here than it is at hitting it somewhere in here, because there's more of this large angle than there is the smaller angle. So most of the light is going to be trapped in here. And the reason for that is this has a really big index of refraction. Okay. In fact, let me go ahead and put this on custom and turn it all the way up to, it doesn't even let me go up to, okay, here, this one winks out there. Okay. So again, everything here, it could get out, but everything in here would be trapped. And this is for an index of refraction of 1.6. Diamond has an index of refraction of 2 point something, 2.1 or 2.2 or something. So it has a really big index of refraction. What that means is it's easy for the light to get into the diamond, but once it gets inside the diamond, it bounces around inside the diamond. Okay, and then if you're, say, turning the diamond, if you turn it so that the light ray is basically coming in at just this right angle, you can get a lot of light to come out at just that right time. And that's what you see as a sparkle. So this is why diamonds sparkle, is because it has such a large index of refraction. Now you know, okay? And not only that, we can do something even a little bit more interesting. So this was, say, I'm going to go to mystery A. Okay, so that was our diamond, say. And let me get it to just where it comes out. Okay, right there. Okay, so if I say take my diamond, which is the mystery A here, I'm not saying it's mystery A, that's what it is. I'm just saying, let's say it's that. If I put it in water instead of in air, so if I change this to water, you notice what happens is now the critical angle is actually much bigger. You're not going to be trapping as much light inside the material. So what this means is that the diamond won't sparkle as much if it's underwater than it would if it's in air. So if you happen to have a diamond ring and you go to a swimming pool and take it under a swimming pool, you should notice that it doesn't sparkle as much under the water as it does above the water. I don't think I've had anybody actually do that, but if you have a diamond ring, I would love to hear about that. I had a student a couple of years ago that had a diamond ring, convinced her mother to take her diamond ring and put it under a water faucet. She said that it did look like it was not quite as shiny, that it was more dull. But I'm waiting for the student that braves taking their diamond ring underwater in a swimming pool. Okay, so I think that's it for the second round of refraction. Does anybody have any questions they want to ask? Okay, it doesn't look like, could I show the formula for the NI on internal reflection again? Do you want me to just, is that what you're looking for? Or did you want me to show you the Excel spreadsheet? Oh, Excel, please. Okay. So for Excel, okay, it should be 1 over the sine of the angle. Remember, you need to change the angle to radians. Okay. Are you still getting a weird answer, Slayton? Okay. Didn't do the 1 over. Yeah, okay. Okay. Anybody else have any questions, comments? Okay, well, I'm going to shut down the recording. I will be in my office until 7 o'clock this evening. I didn't go over inserting the Greek characters in OpenOffice or in LibreOffice. So if it's similar, if you have trouble finding it, let me know, and I would be happy to go over that with you if you're using one of those. The equation for DNI and the percent variation. Here, I can do this. How about we do this? Oh, okay. So the DNI is, it's the standard deviation divided by the square root of the number of data points, which in your case is going to be square root of, actually it's going to be square root of 8. 3, 4, 5. So this should actually be 8, not 11. We'll do as many data points this time. Okay. And then for percent variation, it's just 100 times the uncertainty divided by the average value. Does that give it to you, Abigail? Or I can write it out too, if that would help. Okay, she says she's got it. Okay. Okay. So like I said, I'll be here till 7. You can send me a message on Canvas or send me an email or send me a message through Teams. I'm going to shut down the recording here and then hang up, and then I'll rejoin the meeting back when I'm in my office. Okay? So if I don't hear from you, then let's see. Are we meeting? I guess we're meeting tomorrow, so I will see you tomorrow. So I'm going to close this and shut this puppy down.